All right, this is the second video on the introduction to the capacitance chapter 7. So in this video, we're going to be talking about the work done to charge a capacitor, the charging time of a capacitor, and the discharging time. Now, by the way, if you have not read the slide for this section, it might be hard to visualize. So I encourage you to read the slide first. You don't need to solve all the problem, but it's probably a good idea to have at least an idea of the type of diagram we are going to consider. I don't have enough space on my board to draw the diagram. I will do it for the example for sure. Okay. In this video, just a summary of everything together. So the first thing is the work done to charge a capacitor. The work done is equal to the charge square divided by twice the capacitance. Now note, there's obviously the capacitance equation itself is the charge divided by the voltage. So by using this relationship, we can get the two other relationships. So it is, the work is also equal to the capacitance multiplied by the voltage square divided by 2. Is also equal to the charge multiplied by the voltage divided by 2. All right. So these three formulas are all equivalent. Now, one of the things when we are charging a capacitor is the current is not constant. When we are pushing charge inside a capacitor, charge accumulate. They will push back on the charge and eventually it will have a force as strong as the power supply itself. At that point, there won't be any charge moving in the circuit. So the rhythm at which the capacitor is charging itself is dependent on the time. And to charge a capacitor, to know what is the charge on the capacitor, we can use this formula over here. So the charge as a function of time is equal to the capacitance multiplied by the voltage. Open the parenthesis, 1 minus Euler's number, this is the exponential. Open the parenthesis, minus T divided by RC. And actually, there's a parenthesis missing over here. All right, so note, when we are charging, we are assuming a charge of 0 at the beginning. At time 0, this term becomes 0. When this term becomes 0, this term becomes 1. 1 minus 1 is 0. 0 multiplied by CV, we get 0. So we are assuming at time 0, we got a charge of 0. Now note again, the capacitance is equal to Q divided by V, which means that V is equal to, Q is equal to CV. And if we look over here, after a very long time, this term will get near infinity. This term will be 0. 1 minus 0 is 1. 1 multiplied by CV will be CV. So we will get back to this expression. So at the beginning it is 0. Once it is fully charged, it is this value here. And from the charge as a function of time, we can get the current as a function of time. We simply have to derivate with respect to the time. So derivative of the charge with respect to the time will be equal to the current as a function of time. It is equal to voltage divided by resistance multiplied by the exponential minus T divided by RC over here. All right. So for discharging a capacitor, it is a really similar logic. The formula is a little bit different, but really it is very similar nonetheless. So when we are discharging a capacitor, we assume that there is already an initial charge on the capacitor. This is an important assumption. So the initial charge will be Q0 here. This is the amount of charge that is already on our capacitor. So the charge as a function of time when we are discharging is equal to the initial charge multiplied by the exponential minus T divided by RC. Now note, at time 0, this term is 1, so we are at the initial charge. Makes sense. Once we let the capacitor discharge, well, at some point, we expect that the capacitor will have lost all its charge. So once this term gets very big, this is a minus, a big number, the exponential, it gets near 0, and then we get a 0 charge. Following a similar logic, we can find the current, similar logic to the previous concept, we can find the current as a function of time by simply taking the derivative of this function as a function of time. We get the current is equal to minus Q0, the initial charge, divided by RC, exponential minus T divided by RC. Note there's a minus here. It means that the current is going in the opposite way as when it was charging. Okay, so it makes sense. You're charging in a certain way. The electrons are packed. they are strong, they're repelling. You remove the voltage and then the electrons start flying backward, all right? Just like if you inflate a big balloon, well, you push the air to inflate the balloon. Once you release, the air goes out exactly the other way. It's the same concept here. Now, note this term over here, the term RC, the term RC here is called a time constant. And we use the letter tau, actually it's not T, it's tau. And basically it's the time it takes to discharge the capacitor or charge the capacitor by 36.8%. So note basically once the time here is equal to RC, the exponential, actually it's when T equal RC, the exponential become -1 because it's minus T, which is already equal to RC, so it's minus RC divided by RC. We get E exponent -1 in this case. So this will be 0.368. So it's either 30%, 36% charging or 36.8% discharge in this case. Again, we will be solving many examples using all these concepts. This is just a summary to get a rough idea of what each formula means. As always, the best way to understand this concept is by solving some example, and that's exactly what we're going to do in the next video. All right, so see you there.